today's lecture on Laplace transform. Moving towards next properties. First, we got some properties of Laplace transform. Just before we have learned what is Laplace transform. Laplace transform is Laplace of f of t is nothing but the value of integral 0 to infinity f of t e raised to minus st t. Then we find the Laplace transform of elementary function, that is Laplace of k is k by s. Laplace of e raised to at is 1 upon s minus a. Laplace of e raised to minus at is 1 upon s plus a. Laplace of sin at a upon s square plus a square. Laplace of cos at is s upon s square plus a square. Laplace of sin h at, that is hyperbolic sine, is a upon s square minus a square. Laplace of cos h at is s upon s square minus a square. Laplace of t raised to n is gamma n plus 1 upon s raised to n plus 1 or n factorial upon s raised to n plus 1. These are the Laplace of elementary functions. After that, we see some properties of Laplace transform. First property is linearity property, which says that Laplace of a into f1 of t plus minus b into f2 of t is equal to a into Laplace of f1 of t plus minus b into Laplace of f2 of t. This is called linearity property. Next property we see, that is first shifting property. What is that property? If Laplace of f of t is f bar of s. This is the notation which we have used always. That is Laplace of f of t is f bar of s. Then if f of t is multiplied by exponential, then Laplace is shifted by t, that is f bar of s minus a. It is also known as first translation property. Similarly, we also see second shifting property, also known as second translation property, also known as Heaviside property, is if Laplace of f of t is f bar of s, then Laplace of capital F of t is e raised to minus as f bar of s, where this capital F of t is defined using small f of t by some, it is defined after exists for t greater than a and it does not exist, that means value of function is 0 for t less than a. After that, we see next property, that is multiply by t property. What is this multiply by t property? That is, if Laplace of f of t is f bar of s, then if that f of t is multiplied by t raised to n, then it is minus 1 raised to n dn upon ds raised to n Laplace of f of t, or this Laplace of f of t we may write it as f bar of s. This is multiply by t property. Similarly, divide by t property. If Laplace of f of t is equal to f bar of s, then Laplace of f of t divided by t equal to, if multiply by t then we take derivative, if divide by t obviously we should take integration, but it is from s to infinity of what? F bar of s, or you may write Laplace of f of t with respect to ds, or you may write it as s to infinity f bar of s. One more property that we seen in previous lectures, that is change of scale property. What is that property? If Laplace of f of t equal to f bar of s, then Laplace of f of a t is 1 upon a f bar of s upon t. So, depending upon the examples on this elementary functions, linearity property, first shifting property, second shifting property, multiply by t raised to n, divide by t raised to n, change of scale property, we cover up to this point. In this lecture, if there is a derivative of any function is there, then how to find the Laplace of that function is our question. And if integration is there, then how to find the Laplace of it. So in this video we see Laplace of derivative, that is Laplace of derivative property. So first of all we see how to find the Laplace of derivative, and there is a generalized function, but before that we go one by one. Laplace of dy upon dt is equal to, I will write up to 3 derivatives, that is Laplace of d2y upon dt square, Laplace of d3y upon dt square, and Laplace of d raised to 4y upon dt raised to 4. So remember the steps. You can easily write down in general Laplace of d raised to n y upon dt raised to n. Either you remember this or you may remember the logic behind it. Okay? Simplest way to write down. So here we use Laplace of y bar or y of t. We'll write it as y bar. I remember this one. So, if first order derivative is there, then start from s. If second order derivative is there, start from s square. Third order derivative, then it should start with s cube. Fourth order derivative, then start with s raised to 4. Then obviously nth derivative should start with s raised to n. Then decrease the power of s. So s raised to 1. So next power is s raised to 0, that is 1. So s square, s 1, s cube, s square, s 1. Similarly, s raised to 4, s cube, s square, s 1. And similarly, s raised to n is s raised to n minus 1, s raised to n minus 2, so on up to 1. We have to write this polynomials. Okay? And what about the coefficients quoted? Always first term is positive, remaining all the terms are negative. So give negative sign to all the terms. Yeah. Now next one. Coefficient of first is always y bar of s. Every time first term contains y bar of s. What about next? This is y of 0. If one more term is there, y dash of 0. Y of 0, y dash 0. If one more is there, y dash of 0. If second order cube, third order derivative is there, you have to write up to y dash. If fourth order derivative is there, then it is y of 0, y dash 0, y dash 0, y fourth derivative. What about this? It is y at 0, y dash 0, so on. What should be the last term? If you observe, it is fourth. Sorry. 1, 2, 3. So this should be 1, 2, and this should be 3. One less derivative than this. So if it is n, here should be y is to n minus 1 derivative value at 0. What is this? Y at 0? Y at 0 means value of function at t equal to 0. Or you may say limit t tends to 0, y of is the value of y of 0. Y dash 0 is first order derivative value at t equal to 0. This is given to you. Okay? Now remember this and we apply this for the examples. Most of the time we have to use this menu for application purpose. Okay? Now if instead of y sometimes it is x, then dependent variable is x, independent variable is y, then it should be s into x bar of s minus x of 0. According to dependent variable, Laplace of variable and initial value of that variable should be changed. Don't keep in mind that always it should be y and y. So if it is p, so if dependent variable is p, then obviously it should be s square into p bar of s minus s into p of 0 minus 1 into p dash of 0. So accordingly your value should be changed. It implies that it is a Laplace of p. Okay? So keep in mind, always concentrate on dependent variable. Now we move towards the example. First example is find Laplace of sin t upon t dt. Okay. So if ddt is not there, then we can easily find out sin t upon t and its Laplace. But since first order derivative is there, here f of t is sin t upon t. Then first order derivative is there, therefore it is Laplace of df upon dt. So if Laplace of first order derivative is s into f bar of s minus f of 0 is equation number 1 using Laplace of derivative. Now our aim is f bar of s. What is f bar of s? Is nothing but Laplace of sin t upon t. What is Laplace of sin t upon t? Now it is function upon t divided by t property. Divided by t property says that take an integration from s to infinity of remaining function. Remaining function is only sin t. So Laplace of sin t with respect to ds is equal to integration s to infinity 1 upon s square plus 1 is. Now integration of 1 upon s square plus 1 is tan inverse s from s to infinity. Therefore f bar of s equal to tan inverse infinity minus tan inverse s is equal to pi by 2 minus tan inverse s is equal to cot inverse s is your first one. Okay. Now what is f of 0? Because our next value is f of 0. F of 0 is nothing but limit t tends to 0 f of t is equal to limit t tends to 0 sin t upon t. And we know that sin t upon t limit t tends to 0 is 1. Using both the values, using f bar of s and f of 0 in 1, we get Laplace of d dt of sin t upon t is equal to s into cot inverse s minus 1 is the answer of this question. Okay, shall we repeat? Find Laplace of d dt of sin t upon t. If dt derivative of whatever may be the value, that will be our function. So I consider this as f of t. So Laplace of df upon dt is, using the formula, it is first order derivative. So we should start with s raised to 1. So s raised to 1 into minus 1 f bar of s minus f of 0. Give it equation number 1. Now our aim is to find out f bar of s and f of 0. So finding f bar of s using divided by t property, f 0 is nothing but limit t tends to 0 f of t. We know that limit t tends to 0 sin t upon t is 1. Using both the values in equation number 1, f bar of s is cot inverse s, f of 0 is 1. We get the answer s cot inverse s minus 1. Now, next example. This is one way. Another way, find out the derivative, find out the answer. But after taking the derivative, term will be enlarged, gigantic terms. And so it is better to find out the answer using the properties. Now, find out Laplace of t cube e raised to minus 3t dt. Okay. So, again, ddt of what is nothing but your function. So, let f of t equal to t cube e raised to minus 3t. Therefore, Laplace of d dt t cube e raised to minus 3t is nothing but Laplace of df upon dt. Laplace of derivative, and therefore using the formula it is nothing but s minus 1 because it is first order derivative. F bar of s minus f of 0. Give it equation number 1. Now find out, our aim is to find out f bar of s. What is f bar of s? F bar of s is nothing but Laplace of f of t is equal to Laplace of t cube e raised to minus 3t is equal to Laplace of, again either we use multiply by t property or multiply by exponential property, that is first shifting property. So it is better to use first shifting property. I have already given you that s will be shifted by s plus 3 by first shifting property. So it is equal to 3 factorial upon s raised to 4. Here s will be shifted by s plus 3. Therefore, f bar of s equal to 6 upon s plus 3 raised to 4 is the answer for f bar of s. Now find out f of 0. What is f of 0? F of 0 is nothing but limit t tends to 0 t cube e raised to minus 3t. Put the value 0 into e raised to 0 is 0. Use f bar of s and f of 0 in 1. We get Laplace of d dt of t cube e raised to minus 3t equal to 6 upon s plus 3 raised to 4 minus 0 into, and therefore it is 6s upon s plus 3 raised to 4 will be the answer of this question. Okay. Now, what about second order derivative and third order derivative? Where it actually used? It is mostly used in solution of y of 0 equal to 1 and y dash 0 equal to minus 1 by 2. Find the Laplace transform. Find Laplace transform of is the question. Now actually they don't want the solution of this differential equation. To find the solution of differential equation, first we have to apply the Laplace transform, simplify it and then apply inverse transform. But this is only the half part of it, that is find the Laplace transform of it. So whatever may be the differential equation, that is d2y upon dt square plus y equal to sin t is the given differential equation. Apply Laplace on both the sides. Then we get Laplace of d2y upon dt square plus Laplace of y equal to Laplace of sin t. So we get this is second order derivative. Since it is second order derivative, so for first term we use this bracket. It should start with s square s1. First term is positive, remaining two terms are negative. Along with first term, it should be y bar of s, y at 0, y dash at 0. Right? Plus Laplace of y is nothing but y bar of s. Got it? Equal to Laplace of sin t is 1 upon s square plus 1. So I am just taking the Laplace of each and every term. Laplace of second order derivative is this bracket. Laplace of y is y bar of s. Laplace of sin t is 1 upon s square plus 1. Now, in next step, whatever initial values are given to you, just substitute it. So here we know the value of y of 0 and y dash of 0. Y of 0 is given as 1 and y dash of 0 equal to minus 1 by 2. As y of 0 equal to 1 and y dash of 0 equal to minus 1 by 2. Therefore, we get s square y bar of s minus s, because y of 0 is 1, minus 1 by 2 equal to 1 upon s square plus 1. I am just putting the values of initial conditions. So simplifying this, plus y bar of s equal to 1 upon s square plus 1. So here I have two terms of y bar of s. So in left hand side there are more than one terms containing y bar of s. So collect the coefficient of y bar of s in one bracket. So it will be s square plus 1 and all remaining terms should be sent to right hand side. So it will be minus s will become plus s and this is plus, so it will become minus 1. So again simplifying this, we get y bar of s equal to, now this is in product, shifted into right hand side, it goes into denominator. So it will be s square plus 1 whole square plus s upon s square plus 1 minus 1 upon 2 into s square plus 1 is nothing but your y bar of s, that is Laplace of y, and this is nothing but the answer, that is half part of a solution of differential equation. And this is the application. Your differential equation is converted into algebraic equation using Laplace transform. Got the point? Just see it. Okay? One more for you. Suppose if your differential equation is d cube y upon dt cube plus 2 d2 y upon dt square minus dy by dt minus 2y equal to 0, where y equal to 1, dy upon dt equal to 2, d2y upon dt square equal to 2, and t equal to 0. Find its Laplace transform. See, right hand side is 0, that means it is homogeneous equation. Okay? So, just we have to find out its Laplace transform. So, again, d cube y upon dt square dt cube plus 2 d2 y upon dt square minus dy upon dt minus 2y equal to 0. Apply Laplace transform on both the sides. So Laplace of d cube y upon dt cube plus 2 into Laplace of d square y upon dt square minus Laplace of dy upon dt minus 2 into Laplace of y equal to 0. d cube y upon dt cube is s cube s square s 1 minus 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 y bar of s, y at 0, y at 0, y double dash. This is for your first bracket. Plus 2 into first second order derivative s square s 1 y bar of s, y dash, y at 0, y dash s. Now for third bracket, minus s minus 1, y bar of s, y at 0, minus 2 into y bar of s equal to 0. Got this point? Now put y at 0, y dash at 0, y double dash at 0, that is 1, 2, 2 values at these places. What is the answer? It is s cube y bar of s minus s square into 1, so it is s square minus 2s minus y double dash is also 2, so it is minus 2 plus 2 into minus s minus 2, because y dash value is 2, minus s into y bar of s minus y at 0. Y at 0 is 1, so it is just 1, minus 2 y bar of s equal to 0. Now I recollect the terms of y bar of s in one bracket. So here y bar of s is s cube. Here y bar of s is 2 into s square, so it is plus 2s square. Here y bar of s is minus s. And lastly y bar of s is minus 2. So these are the coefficients of y bar of s. And the remaining are just minus s square, minus 2s, minus 2, plus 2 into minus s is minus 2, s plus 2 into minus 2 is minus 4, minus minus plus 1 equal to 0. Now keeping y bar of s in left hand side, that is s cube minus plus 2s square minus s minus 2 as it is, and simplifying or shifting this term to right hand side, s square minus s square shifted to right become plus s square, minus 2s minus 2s minus 4s shifted to right become plus 4s, minus 2 minus 4 is minus 6, minus 6 plus 7 is plus 1 is minus 5, minus 5 will become plus 5. Therefore, y bar of s is equal to s square plus 4s plus 5 upon s cube plus 2s square minus s minus 2 is nothing but value of y bar of s. At this point, so your third order differential equation, its Laplace is algebraic equation. And this is the beauty of Laplace transform. Here it is. Right now we see that Laplace of derivative, that is Laplace of dy by dt is s into f bar y bar of s minus yx. What happened if there is an integration of f of t dt? What if we want to find out the Laplace transform of integration? So if we are able to find out Laplace transform of derivative, we should able to find out Laplace transform of integration. So new property is Laplace of integral. So this property says that if you observe this, if we take a Laplace of derivative, we have to multiply the Laplace by s. So here, if we take the Laplace of integration, we have to multiply divide by s. That is the property. Here, for derivative we multiply by s, for integration we divide by s. Reverse process. Similarly, if double integration, that is integration 0 to t, integration 0 to t, f of t dt is there, then it is 1 upon s square f bar of s. And what is f bar of s? We know that f bar of s is nothing but Laplace of f of t. At this point, remember this is Laplace of integration. Moreover, remember this limit should be from 0 to t only, not other limits should be acceptable. So now we solve the questions depending upon Laplace of integration. So first example, find Laplace of integration 0 to t cos 3t dt. So here your f of t is cos 3t. We know that Laplace of integration 0 to t f of t dt is equal to 1 upon s f bar of s. Therefore, Laplace of integration 0 to t cos 3t dt is equal to 1 by s Laplace of cos 3t is equal to 1 by s into Laplace of cos 3t is s upon s square plus 3 square. Therefore, answer is 1 upon s square plus 3 square. And if you find out the answer properly by taking the integration, you got the same answer. Because integration of cos is nothing but sine, and sine Laplace is 1 upon a square plus a square. A get cancelled because integration having the denominator divided by 3. Okay. So instead of taking integration and then take a Laplace, instead of that we may use the Laplace of integration property. Second, find the Laplace of, if instead of 1, if there are 3 integration sign, here it is cos h 3t dt dt. What will happen? We know that Laplace of integration 0 to t f of t dt is 1 by s f bar of s. A repeated use of this will give you Laplace of integration 0 to t, 0 to t, 0 to t cos h 3t dt 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 will give you 3 times integration. So this is 3 times 1 by s Laplace of cos h is equal to, for first integration 1 by s, for second integration 1 by s, for third integration 1 by s. So it is 1 upon s cube into s upon s square minus 3 square. Therefore, answer is 1 upon s square into s square minus 3 square is the answer for this question. Now, next question. Now, next question is Laplace of integration 0 to t here main importance is from left to right. You have to position of t is important. Is it inside the integration or outside the integration? Okay. So here we know that Laplace of integration is equal to, because of this integration sign, it is 1 by s Laplace of t sine 2t is equal to 1 by s as it is. Now we have to take the Laplace of this. Now here multiply by t property. Multiply by t property says that it is minus 1 ds of sine 2t का Laplace. Here we use Laplace of integration property. Here we use Laplace of t into f of t property. Now from 3 functions we move towards 2 functions. Now from 2 we come over 1 function only. Now we are able to find out. Now we take minus sign outside. It is ds of Laplace of sine 2t. Laplace of sine 2t is 2 upon s square plus 2 square. There's only 1 function. Finding the Laplace. Now derivative is remaining. Now derivative is an operator which operate on this part only, not on minus 1 by s. And therefore answer is minus 1 by s ds of, I take 2 outside the ds also, it is s square plus 4 raised to minus 1 is equal to minus 2 upon s minus 1 s square plus 4 raised to minus 2 into ds of s square plus 4. Chain rule, applying chain rule, because it is a composite function, we have to take its derivative as well. So minus 1 into minus is plus, so it is 2 upon s raised to minus 2, it will become s square plus 4 raised to 2. Derivative of s square plus s is 2s. So after simplification, we get 4s upon s into s square plus 4 whole square. S's get cancelled, and therefore Laplace of integration 0 to t sine 2t dt is nothing but 4 upon s square plus 4 whole square is the answer of this question. Clear? Now, next question. The next question is Laplace of integration 0 to t e raised to minus 2t sine 3 dt. Now again remember that there is integration property. Laplace of integration multiply by t multiply by exponential. So there are multiple properties we have to apply. Now one more example I want to discuss over it, that is Laplace of, if I change the position, that is minus 2t taken outside the integration, t sine 3t dt. Then what happened? The position of exponential is important here. Here we have to apply Laplace of integration first, and here we have to apply Laplace by first shifting property first. So position of exponential is very important when you solve such type of example where multiple properties are involved. So here when I want to solve this question, goes from left to right, that is we have to tackle first with integration. हमें पहले सामने आता है वो है इंटीग्रेशन, and that's why Laplace of integration 0 to t e raised to minus 2t sine 2t. सबसे पहले हमें प्रेफरेंस देना पड़ेगा इंटीग्रेशन. So for integration we should write 1 by s. Now integration work is over, उसका काम खत्म हो गया, because for that integration we have to take 1 by s, and whatever remaining we have to take its Laplace, that is t raised to minus 2t sine 3t, using Laplace of integration. Now from 4 proper terms we have to come up to 3 terms. Now keep 1 by s as it is. Now out of this 3, here we have 2 properties in our hand. One is multiply by t property and another one is first shifting property. I always say first shifting property is better to use first. So I want to use first shifting property. So it is t sine 3t, and whatever may be the answer, shift s by s plus 2 using first shifting property. Either you may write this or you may write it as Laplace of e raised to at f of t is equal to, now जब तक आप शिफ्ट नहीं कर रहे हो, दिस ब्रैकेट will continue taking up, and now in a bracket now multiply by t property is there, because there are 2 functions now out of this 3. One is removed, that is exponential. Remaining 2 functions are there, that is t into sine 3t. T into sine 3t. So multiply by t property says that minus d ds of Laplace of sine 3t. Because of this multiply by t, we have to take minus d ds. Removing that part, remaining function is only sine 3t. Now see, up to these 3 steps, this bigger example will be reduced to 3 terms, 3 terms will be reduced to 2 terms, 2 terms now reduced to 1 term by applying consecutively 1 by 1 properties. Now we are able to find out Laplace of sine 3t. Find out it. S will be shifted by S plus 2. First take the derivative and then shift, because first we have to do the bracket term. So first of all, is equal to minus, I will take 3 outside the bracket because it is constant, ds of s square plus 3 square raised to minus 1. S will be shifted by s plus 2 is equal to minus 3 upon s minus 1 s square plus 3 square is to minus 2. Again its derivative, I will write it directly as 2s, and here s will be shifted by s plus 2 is equal to minus minus will become plus. This is 3 upon s, 2s upon s square plus 3 square whole square, where s is shifted by s plus 2. Therefore, final answer is 6 upon s. Here s will be shifted by s plus 2. So it is s plus 2 upon s plus 2 bracket square plus 3 square bracket square will be the answer of this question. Now apply one by one property and reduce the last term to single number. Okay. Now, as we discussed previous, I want to change the position of exponential and we see what happens. Okay. Now, in the same example, I just remove this exponential. This is t, integration 0 to t, and taken outside e raised to minus t, outside the integration. Then because of this integration, t sine 3t dt, first we have to apply the Laplace on exponential into function. So here we have to give the preference to exponential into function property, not on Laplace of integration. Okay, because integration will not be applied on exponential. So here Laplace of integration 0 to t, t sine 3t dt, and whatever may be the answer, answer should be shifted by s plus 2 by Laplace of e raised to at f of t property, because we have first made it to exponential. Now Laplace is applied on integration. Therefore, Laplace of integration says that it is 1 by s Laplace of t sine 3t, where s is shifted by s plus 2 is equal to 1 by s. Now multiply by t property here using Laplace of integration property. 1 by s, for this t it is minus dts, Laplace of sine 3t, where s is shifted by s plus 2. Here we have used Laplace of t f of t property. Same property we have used as we used in previous example, but sequence of properties are changed. Because of this, change in answer will be there. Slight change in answer is there. So 1 by s here minus ADS of Laplace of sin 3t is 3 upon s square plus 3 square s shifted by s plus 2. Now I write out this answer. 6 by s plus 2 upon s plus 2 whole square plus 3 square whole square. Now it is 1 by s minus 3 taken outside ddx of s square plus 3 square raised to minus 1. S will be shifted by s plus 2. Therefore, it is minus 3 upon s minus 1 into s square plus 3 square raised to minus 2 into 2s, where s is shifted by s plus 2. S's get cancelled and answer is 3 upon s square plus 3 square whole square, where s is shifted by s plus 2 and therefore answer is 3 upon s plus 2 whole square plus 3 square bracket square. Now this is the answer for this question. Now if I write this question, this is the answer for Laplace of integration 0 to t e raised to minus 2t sin 3t is equal to, and now this is the answer for e raised to minus 2t integration 0 to t sin 3t, and answer is 3 upon 2. Where is 2? Yes, okay, it should be 6. So this is 6 upon s plus 2 bracket square plus 3 square whole square. Observe the change. Here s plus 2 upon s, this term is not there. So change of the position of exponential will give you the change in your answer also, and therefore be careful about such type of example where integration, position of integration and exponential, position of integration and t will give you the change in answer. So whatever will be the first फर्स्ट पोजीशन किसकी है उसको आपको पहला प्रेफरेंस देना है. Okay, so observe this and find out the answer. So now I write some example for you as a homework. Find the Laplace transform Find Laplace transform of t raised to 4 e raised to minus 5t ddt of. Find Laplace transform of triple integration cos 4t dt. Find Laplace transform of integration 0 to t sin 3t dt x into. Find Laplace transform of e raised to minus t integration 0 to t sin 5t dt.